Okay, so in the last lecture, we discussed that if we would like to study the dynamics, that is, how a wave function psi xt changes with time, then we need to write the equation of motion, that is, and in quantum mechanics, that is given by Schrodinger's equation of motion. And in the last lecture, I wrote Schrodinger's time dependent equation of motion. And then we saw that, first let me write the equation. I h cross del psi xt by del t is equal to minus h cross square by 2m del 2 psi by del x square plus potential into the wave function psi. So this was my Schrodinger's time dependent equation, and we saw that if we take a special class of solutions, that is psi xt is equal to psi x and phi t, by substituting this we got that the solutions of the wave function as follows. We got I h cross del phi by del t 1 upon phi t is equal to minus h cross square by 2m del 2 psi by del x square 1 upon psi x plus vx. And because these two equations, here there is a complete time dependence and here there is a complete space dependence, so it has to be equal to the constant, and we took that as energy E. Now, so we got the two equations as I h cross del phi by del t is equal to E of phi t, where we can get the solution for phi t as phi naught e to power minus I e t upon h cross. So this was the time dependence of the solution of the equation. And then by equating, so this was equating by this, and then by equating the second part, we can get minus h cross square by 2m del 2 psi x by del x square plus vx psi x. This is equal to E of psi x. This was my second equation, and here I told you that this equation is obeyed by functions of definite energy. By functions of definite energy. Energy E, and given by psi x, I can write psi ex. So my solution was the solution of the time dependent Schrodinger equation. I can write as psi xt is equal to e to power minus iet upon h cross psi x. And then we made some few nice observations that despite the time dependence, all the physical observables will be time independent, and that I showed you, because the time dependence goes as the exponential, so it goes away. Okay, and then also similarly the probability of finding a momentum p will also remains, it does not change with time. For this reason, the states we call as stationary states. Now I would like to take the time independent Schrodinger equation, which is this equation, and then try to find the wave function and the energy values for different kinds of system. Okay, so let me proceed with that. So we are taking now, okay, just a sec. Okay, so now, yeah. Okay, so let me now try to see the solution of Schrodinger's time independent equation. Okay, and the equation is minus h cross square by 2m psi e by dx square plus vx psi ex is equal to e psi ex. Okay, so we are taking the solutions as the wave function that describe a particle of definite energy E. Now we see that the function psi e, it obeys an equation, and what does it depend upon? It depends upon the potential the particle experiences. So the function psi e, it depends upon the potential it experiences. Okay, so what will happen, for example, in different kinds of system, this potential is same, then according to that potential we can solve this equation and find the wave function and the energy values set. So for the different potential we have a different set of functions and the corresponding allowed energy values. Okay, so we'll try to see, for example, wave function for a free particle. If there are, for example, no boundaries, we would like to write that if I take wave function for a free particle, then if the particle is free, then the potential is 0. So let us take the simplest case of potential Vx is equal to 0. Then my wave function, my equation, Schrodinger equation will become minus h cross square by 2m d2 psi e by dx square plus or is equal to e psi e x. Or we can also write this equation as d2 psi e in a more cleaner way, d2 psi e by dx square. We can divide this whole equation by 2m upon h cross square and also multiply the equation with 2m upon h cross square, and also we can multiply this with negative sign. So we get a much cleaner equation as d2 psi e by dx square 2m upon h cross square e psi e x, here also it's a function of x, is equal to 0. Now what is this? This is a second order linear homogeneous differential equation. Okay, if I assume 2me upon h cross square as k square, then I can write this equation as d2 psi e upon dx square plus k square psi e x is equal to 0. Okay, and the solutions for this equation is well known, that the solution, if we have a second order linear homogeneous differential equation. Okay, so you can note that in the Schrodinger equation we have a second derivative. Okay, so the first derivative d psi by dx and the psi and the wave function should exist. Homogeneous differential equation. So of such a equation the solutions are oscillatory. We know that we get psi of ex as a e to power I kx plus b e to power minus I kx. So the wave functions are oscillatory. and the plane wave, basically it is a plane wave, okay, so which cannot be normalized until we specify some boundary. Okay, so here energy will be h cross square k square upon 2m. Okay, if I would like to plot between E and K, I will get the energy diagram like this. So it will have all the energy values. Now let us try to see, and it's clearly a superposition of two waves with P is equal to h cross k and P is equal to minus h cross k momentum. Okay, now if I put some boundary, okay, then we can normalize the wave function. For now, if I take and put a boundary for this particle, and I take a particle in one dimension box, okay, and I specify the length of the box as L, and the particle cannot go out, so basically it has impenetrable walls. Okay, and inside the box the particle is free, but the particle cannot go out. We can also call this problem as square well problem, square well or infinite potential. Why are we calling this as infinite potential? Because at the boundary I am saying that the walls all are impenetrable, so the particle cannot go outside. So that is why when I take such a box at the boundary, the potential is infinite. And inside the box the particle is free, so my potential is 0, and I have the boundary as, and for the simplicity, let me take the box as one dimension. Okay, so I can specify the potential as V is equal to 0 from x is equal to 0 to L. Now let me try to see 0 to L, and that's all. Now let me try to find out the eigenvalues, that is the energy values, and the wave function which satisfy such a kind of problem. Okay, let us try to solve that. Again, what we will do? We will try to write the Schrodinger equation for such a problem. The Schrodinger equation reads like this. Equation will be d2 psi by dx square plus 2m upon h cross square E minus V psi is equal to 0. Okay, so I am taking in general the Schrodinger equation. Now when I write the Schrodinger equation inside the box, then I know that the potential inside the box is 0. So my equation will become d2 psi by dx square plus 2m upon 2me upon h cross square psi is equal to 0. Okay, psi is a function of x. Is equal to 0 because the potential is 0, and this solution is from when x is 0 to L. Okay, and when the walls are impenetrable, the potential is infinite at the walls, the particle cannot go out, so we cannot write the Schrodinger equation. The wave function vanishes. Now again, this is a second order homogeneous linear differential equation, and I know the solution is oscillatory, but to writing in a simple way, I can which can be very easy to solve, we can also take the solutions as in the terms of sine and cos. Okay, because it will not change the physics. So and also 2me upon h cross square I can take as k square. So my equation will become d2 psi x by dx square plus k square psi is equal to 0. Okay, so I can write my equation as one more step, d2 psi by dx square plus k square psi x is equal to 0. The solutions of this equation I can take as a cos kx plus b sin kx. Now what is our aim? Our aim is to find the constants a and b, so that I can find my wave function, and also to find the allowed energy values. And from this equation of K, I can find the energy values as E is equal to h cross square K square upon 2m, which the result which we got earlier. But now we'll try to see that how the boundary imposes the condition on K. Okay, so now let me apply the boundary conditions. The boundary conditions are, how do we solve the differential equation? By applying the boundary conditions. The boundary conditions are that at x is equal to 0 and at x is equal to L, this is the boundary of my problem, the wave function vanishes. Okay, the particle cannot go out. Okay, so applying this boundary condition, what I can write, that psi is 0 at x is equal to 0, cos 0 1, so and sine 0 0. So what will I get by applying first condition, that x is equal to 0, psi is equal to 0? I will get 0 is equal to a, so my a becomes 0. Okay, and then at x is equal to L, again the wave function vanishes. Then if I substitute there, the wave function is 0 left hand side. I am putting these boundary conditions here in this equation, equation number 1. Sorry, I should put the equation numbers. This is my first equation, this is my second equation solution. Okay, and this is my third equation. So, and these are my boundary conditions 4, 5. Now putting this in equation number 2. Okay, this boundary condition, what do I get? A cos KL, A cos KL plus B sin KL. Okay, now already we have calculated that A is 0. So what do I get? B sin KL is equal to 0. So that this product will be 0 if either B is 0 or sin KL is 0. B cannot be 0. Okay, otherwise everything will be 0. So what do I get? Sin KL is equal to 0, and this implies that sin KL is equal to 0. This implies that KL is equal to n pi, and my K becomes n pi by L. Okay, now from here this is a very nice result, because by knowing the value of K, I can find energy, because already I know that my energy is h cross square K square upon 2m. If I substitute the value of K, I get my energy as, I can put a substitute n h cross square n square pi square upon 2ml square. Now what does this mean? It means that all the values of energy are not allowed. Energy is quantized. Okay, if I want to find the energy of the ground level, I'll put n is equal to 1 h cross square pi square upon 2ml square. So I get a very nice result. The energy is quantized. If I have a particle in a box with infinite potential walls, energy is quantized. This is my first result. Okay, what was my equation number? This is 5. Okay, I can put this as 6 and this 7. Okay, and this is 8. Now what is remaining? The wave function. I know already A is equal to 0, but still I don't know B, because in order to find the wave function, I had the wave function as B sin KL. Okay, KX. K value already I know. Okay, so what is B? B sin n pi upon Lx. Okay, this is not there. This is my psi x. I should know B, then I know the full wave function. Now what else condition I can put to find B? I also know that the total probability of finding the particle inside the box amounts to 1. Okay, and if I apply that, the wave function will be normalized. Now in the probability of finding the particle in space is 1. What is my space now? My space is my box. So I know that I generally put, I have the limits minus infinity to infinity mod psi square dx is equal to 1. But now I have limits 0 to 1 mod psi square dx, this is equal to 1. So if I apply this normalization condition, this is to find B. Okay, these are the energy eigenvalues, allowed energy eigenvalues. Okay, normalization condition. So when I apply this 0 to L B square sine square n pi x upon L dx is equal to 1. Okay, now I have to solve this equation. I can put the equation number, normalization condition. This is 9, 10. Okay, now in order to solve this equation, we can do just a simple integral. Sine square I can put in terms of cos 2a. We all know cos 2 theta is 1 minus 2 sine square theta. Okay, so substituting this, what do I get? Just using the trigonometric relations. I can put as b square 0 to L is constant, it can take out cos 2. Okay, just a sec. Cos 2 kx, na? There is no need to put n pi by L also, okay, because then unnecessarily, because this is a constant, it will not change anything. So I can take sine square kx. So I can write this as, there is no need to write this, 0 to L b square sine square kx dx is equal to 1. Okay, so 1 minus, there will be cos 2 kx by 2. Okay, dx, this is equal to 1. When I do this integral and apply the limits, I get b is equal to, b square is equal to 1 by L and b is equal to 1 by root L. Now I know both the constants and my wave function. By substituting this value 11 back in the wave function equation, I get psi nx is equal to 1 by 2L, sorry, 2 by L, it is small mistake, it will come 2 by L. Okay, root 2 by L, root 2 by L sine, substituting the value of k, n pi x upon L. These are my wave functions. Okay, equation number 12. So equation number 8 that gives you the allowed energy values, and the equation number 12 will give you the wave function. So for a particle inside infinite potential well, will have the wave functions, the energy values as n square pi square h cross square upon 2 ml square. These are my energy eigenvalues. Energy eigenvalues, and the wave function would be root 2 by L sine n pi x upon L. This is, sorry, x. These are the eigenfunctions of the particle. Now if I would like to plot this wave function with x Okay, from 0 to L, then I get that for n is equal to 1, I get the wave function as, these are my walls, from 0 to L, I get psi 1 as this. Then when I plot psi 2, you will see you'll get the wave function like this. For psi 3, the wave function would be, okay, this is your psi 1, psi 2 and psi 3. And if I would like to see the probability of finding the particle inside the box, then I get that, because probability is positive, definite. So from 0 to L, what will I get? The same. For psi 2, mod psi 2 square, I will get like this, and psi 3 I will get like this. This is mod psi square with x. This is your mod psi 1, mod psi 2 square, mod psi 3 square. Okay, that at the ground state, the probability of finding the particle is maximum at the center, okay, and then minimum at the corners of the box. For the first excited state, the probability of finding the particle is minimum at the center and then maximum here. This is L by 2, L by 4, okay, and so on. Okay, so we saw that for a special case, if I take a particle inside a finite potential well, my energy values are given as n square pi square h cross square upon 2 ml square. Okay, more, if L is large, En will be less, so the energy values are closely spaced. Okay, if L is very small, they'll be far. Okay, so we'll try to see and more examples of solving the Schrodinger equation now next by taking the walls finite. Okay, so see you again. Bye.